Okay, so we're going to continue with the Taylor series now. So this section here on interval of convergence, that will be the last thing for class test 3. So differential equations up to and including interval of convergence. Then the second thing for today on evaluating limits, that will be the first thing for class test 4. Okay, so please just make notes of that. Okay, so what is the interval of convergence? So a given function let's call it f, may have a domain being all the real numbers, like your exponential, sine function, cos function, the domain is all of the real numbers. But the Taylor series may only be valid on a smaller interval. Let's say from a to b. Okay, so even though the function can be defined for all real numbers, the Taylor series, being a series, may only converge on a smaller interval. Okay, this is called the interval of convergence. So we'll have a look at one example, and then on Desmos, I'll show you what we mean by interval of convergence. Okay, so the main example for today will be f of x equals tan inverse x. Okay, so last time we looked at finding the Taylor series for this. Remember, we had the trick of integrating 1 over 1 plus x squared. Okay, so let's say we have the Taylor series. So the Taylor series is given by the sum n goes from 0 to infinity, minus 1 to the n over 2n plus 1, x to the 2n plus 1. Right, we covered that last time. What we want to do now is compare the domains of these two functions. So we have the usual arctan function, we know that domain. But this on the right there, that Taylor series, is also going to have some domain. And we want to compare them. Okay, so let's have a look at this on the Desmos here. So in green, we have the arctan function. Notice how it has the full domain. Yeah, so it has full domain of all real numbers. Okay, here in red, we have the Taylor approximation, where this capital N here is 1. So if we substitute that in, that will be x cubed. So it's a quadratic. Okay. As we increase this capital N here, that approximation is going to get better and better, right? We add more terms, it gets better and better. Now notice the domain for the red one compared to the green one as we increase this N. Okay, so we're going to increase the N. Okay, we go. Okay, let's put a dotted line so we can see it a bit better. Okay, again, we've increased it to 610 there. We can increase it all the way further and further, up to 1,000, but it never goes beyond those bounds there. Okay, so again, I'll zoom in here. So the red, that's the Taylor series, but notice it never goes beyond the interval minus 1 to 1. You can add as many terms as you like, it will never go past that. That is what we refer to as the interval of convergence. So from minus 1 to 1, you see they perfectly overlap, no problems. Outside the interval, very big problems. Okay, so this interval here, minus 1 to 1, that's the domain for the Taylor series, which we call the interval of convergence. Now, for other functions, it might not be minus 1 to 1, or be something else. Sometimes the domain for the Taylor series is also all the real numbers. That's possible. Okay, but the idea is to find what this interval is. Okay, so in general, it's going to be some smaller part. Okay, so here we can see it's from -1 to 1. Let's do the calculation and check that. Okay, so what we want to do is find the x values for which the series converges. And we know how to check if something converges. So we want to find the possible values of x for which the series converges. Okay, now we know there's 10 methods to work it out, but what we're going to use for this example and what we're going to use for every example is the ratio test. Okay, so for the interval of convergence, please do not try use something else. Okay, you will always use the ratio test to find the interval of convergence. Okay, so what do we need to do for the ratio test? We find the an, whatever's in the sum there. We take the limit of an plus 1 divided by an, and when will that converge? When it's less than 1, exactly. Okay, so we're going to have the limit as n goes to infinity, an plus 1 over an must be less than 1. If it's less than 1, it converges. If it is outside of that, it does not converge. Okay, so we want to find the x values for which it converges, so we force the limit to be less than 1. Okay, now we just substitute and then evaluate. So we're going to have the limit as n goes to infinity, absolute value, an plus 1. So wherever we see an n, we put an n plus 1. So that will be -1 to the n plus 1, x to the 2n, but now n plus 1, all over 2n plus 1, but now the n is n plus 1. Okay, so again, wherever we had an n, we now put n plus 1. And we can see that in the brackets there. Now we divide by an, or in other words, multiply by the reciprocal. So that will be 2n plus 1 at the top. And then at the bottom, we still have the -1 to the n, x to the 2n plus 1. And we're going to force this to be less than 1 because we want to find where does it converge. Okay, so all of these examples will be set up the same way. So you set up the limit for the ratio test, you make it less than 1, and what we want is those x values. There's the x at the top there, x at the bottom. We want to solve for that. Solve for x. Yeah, that's the goal. Okay, now we just treat it as a normal limit problem. So first of all, we've got the absolute values. So the -1 at the top, -1 at the bottom, they can go. Absolute value will get rid of those. Okay. Then the n plus 1 brackets, we can expand that out. So this is going to be the limit as n goes to infinity. We can keep the absolute value there. So x to the power of all of that, we can expand that out. So that will be x to the 2n plus 2 plus 1, so plus 3 times. Then we've got the 2n plus 1 left over there. All over. Then the bottom part, we've got 2n plus 2 plus 1, so 2n plus 3. And then again, we've got this x to the 2n plus 1. And again, we still want it less than 1. Okay, a few more things will cancel. So in the top, we have x to the 2n. In the bottom, we have x to the 2n. They can go. Then we have x cubed at the top, x at the bottom. So we'll have x squared at the top. Okay, so we got x squared. And then we still got that 2n plus 1. And then the 2n plus 3. Okay, and the other x's we cancel top and bottom. Next, the x squared, we can take it out of the limit. Okay, because the limit is with n, so the x we just take out. So that will be x squared. The limit as n goes to infinity. And we can drop the absolute value now. We know everything's positive, or you can keep it there. That's up to you. So we have 2n plus 1 over 2n plus 3, and we still want this less than 1. Okay. Now doing this limits, easy enough. 2n at the top, 2n at the bottom, so that's just 1. So we end up with x squared is less than 1. Now, another way of writing x squared is less than 1. So this is equivalent to saying minus 1 is less than x less than 1. Okay. Because if x squared is less than 1, then x must lie between minus 1 and 1. Okay. And this interval here from minus 1 to 1 is exactly what we have here from minus 1 to 1. Okay, so we can write the interval of convergence. Okay, so minus 1 to 1, or you can write it as minus 1 to 1 as an interval. Okay, either is fine. I can see what you mean. Yes. Yes, it must be as an interval. So this x squared less than 1, you need to then convert it to some number less than x less than some number. Okay, and I'll explain that now in a bit. Okay, so let's say we have a general Taylor series. General Taylor series. So this is given by the sum. N goes from 0 to infinity. The nth derivative at a, okay, can be at some point, over n factorial x minus a to the n. Okay, so say we've got some general Taylor series like this, and we end up with the following interval. So you do all the, this part here, all of this stuff here, the ratio test, you do all of that, and let's say you end up with the following. So you'll have x minus a is less than some number r. Okay. So this is after you've done all of the work. You end up with this. Okay, that r over there that you work out, that is called the radius of convergence. Okay, so it's just a little bit of terminology. So this is the radius of convergence. Okay, and if you want to write this more like an interval, we can do that. So this will be a minus r is less than x less than a plus r. Okay, so it's the radius of that interval that we have. For example, you can draw a number line here, the x values. So here we have a. Remember the Taylor series centered at a. Then the start of the interval will be the radius amount to the left and the radius amount to the right. Okay, so that is the radius there, and that's the radius there. Okay. So it's like a one-dimensional circle. So you have the center point at A, then the interval will be A minus R on the left, and then A plus R on the right. Okay, and that's called the radius of convergence. So we A minus R to A plus R. Okay, so with that, we can look at this previous thing here. So from minus 1 to 1, the center point is A is 0, right? Because we did this at 0. So A is 0, and the radius will be 1, because it will be 0 minus 1 and 0 plus 1. Okay, so we have A is equal to 0, R is equal to 1. So you could write it as A minus R to get minus 1, A plus R to get the 1. Okay, A minus R, A plus R. Okay, so that was for the specific example, but in general, you'll have something like this. Okay, so whatever your A value is from your Taylor series, minus R, and then whatever the A is from the Taylor series, plus R. Okay, and this comes from the ratio test. You'll see that. Okay, and then just a bit of terminology. Okay, if the interval of convergence is all of the real numbers, which we'll see in the next example. So say the interval of convergence is everything. Okay, if that's the case, then we say that the radius of convergence is infinite. Okay, so if the interval of convergence is all the real numbers, then we say that the radius of convergence R is infinite. Okay, so it's like A and then all the way to minus infinity, and then A all the way to plus infinity. So it covers everything. Any questions on the terminology? So you're fine with what an interval of convergence is and what a radius of convergence is. Okay, let's have a look at another example. Okay, so we have f of x equals e to the x. Okay, so we know the Taylor series for this already, so I'm not going to repeat that. So we have the Taylor series. We want to know what is the interval of convergence, what's the radius of convergence. So let's write out the Taylor series. So e to the x, that's the sum, n goes from 0 to infinity. What do we have in front? It's 1 over something. Yeah, 1 over n factorial. Okay, and then we have x to the n. Okay, so that's the Taylor series. Either it will be given to you or you need to work it out in a previous question. So given this, we now want to find what is the interval of convergence, what is the radius of convergence. So how do we do that? Well, we set it up as the ratio test and have the limit value be less than 1. So we're going to have the limits. N goes to infinity, an plus 1 over an. We want that to be less than 1. Yeah, and then we just substitute from what's given there. So this will be the limits as n goes to infinity, absolute value, x to the n plus 1, because we replace n with n plus 1, over n factorial, but we replace it with n plus 1, times, and then we flip it around. So the top will be n factorial, and the bottom, that will be x to the n. And we still want this to be less than 1. Okay, we can simplify. At the top, we have x to the n. At the bottom, we have x to the n. They can go away. So we're left with x at the top. So this will be the limits as n goes to infinity, absolute value. So now we're just left with x up there. N factorial over n plus 1 factorial less than 1. Okay. Now the factorials we need to get rid of. But we know n plus 1 factorial is n plus 1 times n factorial. So we can write that and then cancel with that top one. So that will be the limits. N goes to infinity. So we still have the x there. We still have the n factorial. But this bottom part will be n plus 1. And then n factorial. Okay. So the factorials, they can cancel. Okay, then the x we can take out, and then we can do the limits. Remember, we need to keep the absolute value on x. Okay, we don't know if it's positive or negative, so when you take it out of the absolute value, you need to keep the absolute value there. Limits n goes to infinity, 1 over n plus 1. Here we can drop the absolute value because we know that's always positive. Okay, or you can keep it there. That's fine as well. Okay, now something interesting is going to happen here. What happens when we take the limit? Goes to 0. Good. Yeah, so that goes to 0. That should be a 1. Okay, so we have 0 less than 1. Now the question is, which we had at the beginning, we want to find the values of x. So for which values of x over here is 0 less than 1? All of them. You can substitute any value of x, but 0 is always less than 1. Okay, so here, for which values of x is 0 less than 1? Yeah, but that's always true. So this converges for all values of x. The series converges for all values. You can substitute whatever you like into that second to last line. You will always get 0 is less than 1. Okay, so this is true for all values of x. Okay, so that means it goes all the way from minus infinity to plus infinity. Yeah. And if you have x going from minus infinity to plus infinity, we can also say that the radius of convergence is infinite. Yeah. We can see this on Desmos like this other one. Okay, so let's put in e to the x. So we got that in purple there. Then we've got the sum. N goes from 0 to capital N. 1 over n factorial x to the n. Okay, let's say we start at 1. Let's go to 1,000. Okay, so here n is 1. So it's just a straight line. Let's increase, see what happens. Okay, we have to zoom out there. Okay, so you can see the overlap. Okay. Over here, it doesn't overlap anymore. Okay. But we just increase n, and then you can see it starts going further and further. Okay, we can zoom out. Oops. Quite a bit there. Can't really see. Let's put the dots back. Okay, you can sort of see it there. But then there's more of the overlap. Okay, so as you increase this capital N, the overlap goes across the whole graph. Okay, so you can try it out here for different values, and you'll see. Okay, so for homework, try the same thing, but for sine and cosine. Okay, so calculate the radius of convergence, the interval of convergence, and then check your results. Okay, so homework. Repeat for sine of x and cosine of x, and check the results. Right. Any questions on this before we move on? You're good. Okay, so that will be it for the class test 3. Okay, so class test 3 up to and including this homework part. Okay, so the next thing, applications of Taylor series for limit evaluation and differential equations. We'll start that now. That will then be the first question for class test 4. Okay, so applications of Taylor series. Okay, so we'll look at number 1 today for limits evaluation. That will be on the quiz for next week. Okay, this. And then the second one on differential equations, we will cover that next week. Okay, so for the quiz again, for the written parts, question 1 will be find the interval of convergence for some series. Question 2, evaluate the limits. Yeah, it'll be something like that. Okay, so we're going to do this by example. So let's have a look at number 1. So we've seen this limit before. We've done the proof for it. Now we're going to do it using Taylor series. And we'll see it's going to be much easier to do. So we're going to have the limits as x goes to 0 of sine x over x. Yeah, so we all know what this limit is. What is it? 1. Good. Yeah, so let's show it using Taylor series instead of that proof we looked at last year. Okay, so firstly, what do we notice? Here we have x is going to 0. So in the limit as x goes to 0, we know x is getting smaller and smaller. Okay, so that's the first thing. Okay, so here x is going to 0 means x is getting smaller and smaller in that limit process. So we know x is getting smaller and smaller. Let's see how that affects the Taylor series of sine x over x. So we have sine x over x. Okay, we know how to find the Taylor series for that. So that's going to be the sum. N goes from 0 to infinity. We're going to take the Taylor series for sine. Remember, it was the one with the odd terms, and then divide it by x. So that will be minus 1 to the n over 2n plus 1 factorial, because we only have the odd ones, x to the 2n plus 1. And here on the side here, we are dividing by x. So we divide by x. Yeah, and we can simplify this a little bit. So this will be the sum. N goes from 0 to infinity, minus 1 to the n over 2n plus 1 factorial. One of the x's at the top and the bottom, that will cancel. So we have x to the 2n. So that's the Taylor series. Let's write out a few terms from this. And again, notice what happens when x gets smaller and smaller. Keep that in your mind. So this is going to be approximately equal to, and we'll write out a few terms. So this is going to be 1. When n is 0, we get 1. Minus 1 over 6 x squared plus 1 over 120 x to the 4, and so on. There's some other terms. Okay. But again, keep in mind, x is small. Okay. Now, if x is small, x squared is going to be even smaller. X to the 4 will be even smaller than that. Every term afterwards will be smaller than the previous term. So what happens in the limit when x goes to 0? What happens to x squared? X goes to 0, and I'm looking at x squared. What happens? Goes to 0. And x to the 4 goes to 0. And everything after that will also go to 0 in the limit as x goes to 0. So, on the left and the right, let's just put limit x goes to 0, and on the right we just get 1. So here we have the limit x goes to 0, which we did on that right side there, of sine x over x is equal to, what's left over after we take the limit of the right-hand side? Just 1. There we go. So, no need for that complicated proof we looked at last year. We just write out the Taylor series, and then we take x to 0. Right. Any questions for this first example? All clear. Okay, let's look at a few more. So that was example 1, example 2. Okay, and the idea is the same. We're going to get some complicated function, and we're going to replace the function with its Taylor series, and then take a few terms. So example 2, we have the limit, x goes to 0, x minus the natural log of 1 plus x over x squared. Okay, so for this example, what happens when x goes to 0? The top is going to go to 0, the bottom's going to go to 0. You would have to use L'Hopital's rule. Okay, now we're going to try to do something else. So instead of doing L'Hopital's rule, we're going to use this Taylor series approach. For homework, do L'Hopital's rule. It'll be good practice. Okay, so what are we going to do the Taylor series of? Well, x and x squared, that's pretty simple as is. What about the natural log? We can find the Taylor series for that. So the natural log of 1 plus x. We did this last time, so I'll just write out the series. This is approximately equal to x minus 1/2 x squared plus 1/3 x cubed minus 1 over 4 x to the 4, and so on. Remember, we got that alternating. It was x to the n over n, and it alternated. Okay, so that's the Taylor series for the natural log. Let's substitute the Taylor series into the limit, see if it makes it any easier. Okay, again, the idea is to replace the complicated functions with their Taylor series. Okay, so we're going to have x minus the natural log of 1 plus x all over x squared is now approximately equal to, because we're using an approximation there. The top is still going to be x minus, and then instead of the function, we're going to put in its Taylor series. Yep, that's enough terms, and then dot, dot, dots. Okay, you only need a few. Okay, and this is still being divided by x squared. Okay, so what happens to the top there when we simplify? So this is going to be approximately something. In the top, x minus x, that's going to go away. Then we're left with 1/2 x squared divided by x squared. So that's going to be 1/2. Plus. Then we're going to have the 1/3 x cubed divided by x squared. So 1/3 x. Plus, and some other terms we don't care about. Okay. So again, what did we do? We took our limits and the complicated function we replaced with the first few terms of the Taylor series. We simplified and we've got this new sum at the bottom. Now on the left and the right, we then take the limit. Okay, so this was x minus the natural log 1 plus x over x squared, and that is approximately that. Okay, so let's take the limit. So we're going to have the limit x goes to 0 of x minus the natural log 1 plus x over x squared is now equal to, because we're going to take x to 0. When x goes to 0, everything in that bracket there has an x. So all of those terms are going to go away. Okay, every single one in the bracket has some x with it. That goes away. What are we left with? 1/2. That's our limit value. Okay, and again, for homework, please check with L'Hopital's rule to see if you get 1/2 as well. Okay, last example for today, number 3. Okay, so here we have the limits. X goes to 0. 1 minus cos x over 1 plus x minus e to the x. Okay, you could probably guess what we're going to do here. So cos, that's pretty complicated. We're going to replace that with its Taylor series. E to the x, we're going to replace that with its Taylor series. And then it will simplify nicely. Okay, so let's do that. So we have 1 minus cos x over 1 plus x minus e to the x. This is approximately the same thing as if we replaced cos and e to the x with its Taylor series. So in the top, we have 1 minus. Let's put in the first few terms for cos. So that will be 1 minus 1 half x squared plus 1 over 24 x to the 4. And then there's some other ones. We don't have to worry about that. Okay, and in the bottom, the 1 plus x, we're going to keep that at the bottom. Minus, and then the e to the x, we're going to put a few terms of that. So that's going to be 1 plus x plus a half x squared plus 1 over 6 x to the 6. Cubed. And so on, but we don't need more than that. Okay. So again, cos x we replaced with the first few terms for that series. E to the x we replaced with the first few terms of that series. Now we can simplify this a bit. So in the top we have 1 minus 1, so that's going to go away, and we're left with the rest of it there. And in the bottom we have 1 plus x minus 1 minus x, so that goes away. So what do we have in the top? It's going to be 1 half x squared minus 1 over 24 x to the 4, and some other terms we don't have to worry about. Okay, what about in the bottom? Okay, the 1's cancel, the x cancels. The next thing is the half x squared. And some other terms we're not worried about. Okay, so we end up with this. So what happens now when we do the limit? So we're going to have the limit as x goes to 0. Okay, so on the left side, we keep the function we're given there. Okay, now on the right side, we're going to see what happens when x goes to 0. Again, x going to 0, that means x is small. So x squared is pretty small. X to the 4, that's even smaller. And everything after that, we just ignore. Can just ignore all of that. Okay, let's look at the bottom. X squared, pretty small. X cubed, that's even smaller. Everything after that, we ignore. Yeah, that's all gone. So we have half x squared divided by minus half x squared. What's the limit? Minus 1. And that's it. Okay, and again, for homework, check using L'Hopital's rule. Right, you just have to do the derivative once there, and then it'll simplify. So homework, check with L'Hopital's rule. Yeah. Any questions for this one? Yeah. Yeah, because x is small already. X squared is smaller. X to the 4 is practically 0. Anything higher, we just cross out. That makes no difference. We won't have that. No. Yeah, this will be just x being small. The reason is if x is small, we can cancel, and then it's nice. If this was x going to infinity, then the whole top will be infinite, the bottom will be infinite. We're stuck. Okay. Yeah, so let's make a note for that. Note x must be small. Okay. But the questions I give you, obviously they will be small so that you can do the problem. But if you see this next year, your lecturer is not going to tell you if x is small or not. All right. Any questions? No, good. Okay. So just a quick summary for the quiz so you can prepare. The MCQ will be matching up the functions with their Taylor series. It will just be by inspection. So, I gave you the ones to put a box around. It'll be like those. So you'll have e to the x and you have to match it. Or you'll have sine x and you have to match it, or cos and you have to match. Okay. All of them you've seen before. There's no funny things. It's just matching from what we've done. Okay, so that's the MCQ. Then the written, number 1, is going to be finding the interval of convergence for some function, whatever it might be. And then the second part is evaluating a limit using this method. Okay. Sorry. So the first one, finding the interval of convergence. So you're given some function, let's say arctan, like we had at the beginning here. Let's say this one here. Okay, so you're given something like this, and then you need to do the ratio test to find the x values. Okay, that'll be the question 1. And then the question 2 will be something like this. Okay, with like sine or cos or something that we've covered. Okay, so you won't get some function that we haven't done the Taylor series for. Okay, so it will be like sine, cos, e to the x, those ones that we put the box around. Okay. Any questions on that? No. Okay.